Hello, and welcome to today's presentation on UVM-based simulation environment for Ibex RISC-V CPU core with Google RISC-V-DV. In this presentation, we are going to be showcasing the simulation of the Ibex core, which is a two-stage in-order 32-bit RISC-V processor. It has been designed to be small and efficient, and this uses a UVM test bench, which uses the open source RISC-V-DV random instruction generator, which generates compiled instruction binaries. We then load these binaries into a simple program, which then stimulates the Ibex core in Riviera-PRO to run this program in that memory. So we are using Riviera-PRO for the simulation of the UVM test bench for verification of the Ibex core. And then we compare the Ibex core simulation trace log from the RTL simulation against a golden model generated by an instruction set simulator, which is like a Spike or OVP sim. This is the test bench architecture of the verification environment. And as you can see, we have these rounded blocks, which are SV dynamic objects or like classes. And we also have the square ones, which are actual SV modules, like a module or an interface. So these are the static ones, and these are the dynamic ones. And this is our environment. You can see the test, which instantiates the environment, and you have agents under there, and you have some virtual interfaces connecting with the different interfaces that are found on the Ibex core. And the blue folded corner boxes, these represent some kind of code within the environment. So this could be some kind of a task, like in this UVM run task or something like that, or in the DUT, it is the actual code, like from the initial block. So the test bench is created based on its usage of the RISC-V-DV random instruction generator developed by Google. And there are two memory interfaces agents in there, and which are instantiated within the test bench. And one of them is the instruction fetch interface, and one of them is for the load store unit interface. And these agents, which run the slave sequences, wait for memory requests from the core and then grant the requests for instruction and data. There is also an interrupt interface agent, which is used to drive stimulus onto the Ibex core's interrupt pins randomly during the test execution. And the test bench also instantiates a single instance of the memory model that it loads the compiled assembly test program into at the beginning of each test. And this serves as a unified instruction and data memory that processes all requests from both of the memory interface agents. The tests are located in the tests and sequence library, and this is the main source of external stimulus generation and checking for this test bench, because the memory interface sequences simply serve the core's memory requests. So this is where all the test stimulus and generation takes place. The tests are all extended from core Ibex base test, and they manage the entire flow of a single test from loading the compiled assembly binary program into the test bench memory model to checking the Ibex core status while running the test, and also handling timeouts. And the sequences here are used to drive interrupt and debug stimulus into the core. The goal of this test bench is to fully verify Ibex core, and we use Riviera-PRO to run that simulation and analyze results and coverage data. And we also use it to visualize the UVM environment as well. So the prerequisites for running this is a system Verilog simulator that supports UVM, like Riviera-PRO, a RISC-V instruction set simulator, like for example, Spike or OVP-Sim, a working RISC-V tools chain, and this is used to compile, assemble the generated programs before simulating. So let's go ahead. So this is how the RTL and the instruction set simulator co-simulation flow looks like. And we have the make that will generate the random instruction generator, and we use the RISC-V tool chain to assemble that, and we load both the ISS sim and RTL with that test binary, and then we run the simulations, and then we compare both the simulation using a post compare script, and this is done in Python. And we get the results so we can see if both the simulations are giving the same output. So that's what this emphasizes, is running the simulation. We use the random instruction generator to generate the compiled instruction binaries, and then we load them into a simple program, a simple memory model, which the test bench uses to stimulate the Ibex core to run this program on the memory. And we use the same binaries to run the instruction set simulator. And now we compare the ISS trace log to the RTL simulation log to check for correctness. So let's go ahead and take a look at this demo. So let me switch over the screens so we can take a look at my other screen. All right, so here we have a nice how-to file that we created in order to run this RISC-V Ibex core simulation. And the first thing you need is to get the Ibex version that we tested this on. And then you need to also have the RISC-V toolchain, and you can download it from here. And you also need to download and set up the ISS like Spike or OVP-Sim, and you can do that. But for the sake of this presentation, we are going to assume that this is all done, because that's gonna take a little longer to do. So we will just assume we have that, and we will just run the simulation to see how that looks in simulation. So the first thing you need is a Linux environment. Could be a virtual box or could be a native Linux machine. And the first thing we want to do is go to the core Ibex directory under the design verification UVM subfolders. So that's where the tests are run. And then we use make files to run the tests. So we have a couple of commands here. So if you look at this command, it's to run a make file, and you selected the simulator to be Riviera-PRO. We selected the ISS to be OVP-Sim, and we selected the test to run the RISC-V arithmetic basic test. And we are only going to run it for one iteration because we want to keep this simple and quick. And we want to just run this to show you how the co-simulation works and how you see the results. So let's go ahead and run that. So right now it is generating and compiling the RISC-V instruction from the random instruction generator. So it's running the random instruction generator. It generated that test, and now it is going to run that in the ISS. And after that, it's going to start up Riviera-PRO in batch mode and then run the simulations in that. So it's running the OVP sim now for that basic test. And it's finished that, so now it's starting to compile in Riviera-PRO. And now it's initializing the simulation. And all the simulation is run in the background, so you don't see the simulation log here in the console, but you would see the final results. And the final results are here. So we have one passing case, and it has compared both the files from the RTL sim and instruction generator sim, the OVP sim, and then it compared that together, and it says it's matching, so the test passed. So this is nice when we are trying to run regressions and batch mode simulations. But the real benefit of using Riviera-PRO is from using the GUI in order to take a look at your results and analyze the data. So for that, let's go ahead and run the simulation in the GUI. So in order to do that, we need to add in a certain options like the SimOps. We want to add the dash GUI option, and I'm also enabling coverage. So the coverage I will add in the compilation, and also I will add it in the simulation side as well. So let's go ahead and run this. So it recompiles because we made changes to the compiler options. So it's going to recompile, and then it'll go through the same steps. And if you notice, every time we run it, it generates a new random seed, so makes the test different every time. So now it's doing the same thing. It generated the test of the instruction generator, and now it's going to run the OVP sim. And then once that's done, it will recompile the RTL and then restart the simulation. And this time it should start up in GUI. So there you go. So the GUI simulation finishes, and now let's switch to the debug perspective so we can take a look at some of the details of the hierarchy and the simulation. So one of the first things I want to show you is the classes window. So the classes window is very useful when you are working in a system verilog class-based environment where you have different classes and instantiations. And this classes window gives you like a single location where you can take a look at everything. And if you expand any of those, you can see where is that class derived from, what methods are in that class, if there are any inherited methods, and same with the property, what are the properties it has inherited and all of that. And you can also see if anything has like a derived class and a base class. You can see all of that. And same with the methods, you can see inherited and the methods and properties defined in that particular class. And you can navigate, so from one class to the other, and that makes the navigation easy. And then you can also go to the source file and declaration as well. So that is our classes window. The next thing I want to show is the UVM graph. The UVM graph is very useful if you are new to UVM environments or if you are trying to learn somebody else's UVM environment. So this is automatically generated using Riviera-PRO, and it is generated based on how you write your UVM environment. There is no additional coding required to generate this graph. And as we talked about, we have two memory interface agents, and we have one interrupt interface agent. And this is how they are connected. And if you expand any one of those, you can see how the different ports and the different FIFOs are connected within those components of the agent. And we can expand them more, and we can take a closer look at how everything is connected together. And if there are anything that's not right, you can take a look here and just try to understand how the various components get connected inside your UVM environment. If there are any missing connections and stuff like that, you can analyze that from here. And this also serves as a very good documentation tool. So if you want to export, you can export into a file, so you can use it for documentation as well. So let's move ahead and go back. So that's the UVM graph. The next thing I want to show you is the assertions window. So assertions window, the way it works is it shows you all the assertions that are part of your simulation. It could be like from different files, but it is shown in a single location. So you can see all your assertions from one location, and you don't have to worry about going into different files and trying to find those. And you can also see other data, like if this assertion has passed vacuously or non-vacuously, if it's active or inactive, and if how many times it has been attempted and how many times it has been failed. So there's a failure count, and there's also a pass count, and there's time as well when it has happened. So all this information is very useful when you're trying to debug a failing assertion. So you can take a look here and see why it is happening or why it's not running. So that's the assertions viewer. So now let's go ahead and take a look at our waveform viewer. And in order to do that, I will have to restart the simulation. So the simulation has been restarted, and I will add all the signals from the DUT to the waveform. And now we can run the simulation to see what's going on the waveform. So let's go ahead and take a look. So I added all the signals. So you see the input and output ports as well as the internal signals from the DUT. And I can expand from the time the reset goes around the time the reset goes high here. And we can see the instruction address and what the instruction is. And we can take a look at the data coming in as well. And we see if there is any output data there on the output port. And we can see if that is going into the design, and we see the same data being transferred into the internal signals of the design as well. So in here in the waveform, we have a lot of nice features, like you can add multiple cursors to the waveform. You can add additional columns here, like if you want to look at the hierarchy or the type of the signal and all of that. And you can see the hierarchy here. And you can also right click, and there are other options. So you can create virtual groups. So you can group signals by different types, or if you want to group them together, you can do that with virtual groups. You can create a virtual array. So a virtual array, if you want to split up a bus into different parts, you can use that for like creating a virtual array. And you have now a virtual array with bits 31 to 18 only. And then you can rename that, and it will also show you the equivalent value of those bits together. And if you select the right click on a signal, you can set their properties from either changing the radix or to also changing it into an analog representation. Instead of just a digital value, you can look at it in an analog representation as well. And we also have some nice features for navigation on top, like placing bookmarks, expanding delta cycles, and also browsing the waveform using falling edges, rising edges, or events and stuff like that. You can browse the waveform using that as well. So that's our waveform viewer, and let's go ahead and take a look at some of the coverage options and the coverage that we have available. So for code coverage, we need to, the coverage data is there. Once the simulation is run, we just need to run a few commands to generate a HTML report. And I have a script for that already. I'll just execute that. And now we should have the results generated. And let's take a look at that results file. So this is our code coverage report. And in here you can see the components in different ways. You can see it in a hierarchical hierarchical mode, where you see the design hierarchy. Or you can see it in like a flat, all units in one location. Or you can see it by files as well. And when you select any level in the hierarchy, units or files, it will show you the corresponding coverage. So in this case, it's statement coverage is selected. So it will show you all the statements. And you can select on a line, and it will take you to that line. And you can see the lines in green are covered. The lines in red are not covered. You can see the summary for that particular component. And if you select on the cumulative, and you can see the summary for the whole design. And every time you change the view on the hierarchy, everything else changes to match that component of the hierarchy. And now you can look at the code as well to see which one. So in this case, we have the line coverage or the statement coverage saying these statements are not covered. And same thing, if you go to branch, you can see the branch coverage of that particular line. If it's a if-else statement, it will show you how many times it's true and false. And if it's a case statement, it will show you how many of the possible cases. So in this case, there are 241 cases and only 25 of them have been executed. So it will show you all of that information in the branch coverage. And also, if you go to assertion coverage, if a file has assertions or a component has assertions in them, it will show up here, and you can see these three assertions have been executed, but this one has not been executed yet. So you want to run the case or run another case to execute, make sure that assertion is running. And under, if there are different components, you can take a look at the different types of coverage for those components. And the Cumulative will break you down in just the total coverage for the whole design. So that's how code coverage looks in Riviera-PRO, and that brings us to the end of the presentation and the demo, or the demo part of the presentation. So let's switch back to the slides so we can take a quick look at and wrap up the presentation. All right, so that was the demo, and now in conclusion, we can use Riviera-PRO to run the UVM-based simulation environment for the Ibex core, which is a RISC-V processor core, and we can use the advanced debug tools available inside Riviera-PRO to run and look at your waveforms. You can look at your UVM graphs. You can look at classes window for navigation. And you can also use assertions and covers window to look at assertions from a single location. And we can also use coverage tools available in Riviera-PRO for coverage analysis, like code coverage we saw and assertion coverage. But you can also add system Verilog functional coverage to the environment, and that will allow you to look at system Verilog functional coverage. And also, if you have any state machines, you can add FSM coverage as well. So thank you for joining us today for this presentation. And if you have any questions, you can reach out to us at these links below. And thank you, and you have a very good day.